Hi, Kaiweets sent in another item for me to review, and this time it is a 30 volts 10 amps switching power supply. The model number is 3010F, which is similar to quite a few other power supplies with different brand names you can find in places like Amazon and Banggood, for instance. I suspect the circuit boards used in many of these 30 volts 10 amps power supplies are probably very similar, if not identical, if past experience holds. But of course we'll have to do a teardown to confirm that later. Now the market for these sub $100 power supplies are very competitive and are crowded with many options hobbyists can choose from, so we'll have to take a look at how good this power supply really is. Being a switching power supply, the first thing you notice is just how light this thing really is. And if you look through the venting holes on the side, you will notice that how empty it really is inside. In fact, I think you can easily fit everything into a much smaller package by mounting the main board sideways or vertically by the look of it. And I suspect that's exactly what some of those 3010 model variants did. The power supply itself also came with these rather short and stiff leads, which of course they will work, but I think it will have significant voltage drop, especially in high current applications. Of course, leads are one of the areas they can easily cut some costs, as a pair of these silicone molded leads with higher current ratings, like the ones I have here, this will definitely almost certainly cost a few dollars more. And now let's power it on and we'll take some basic measurements. And not sure if you heard, the first thing I noticed is as soon as you power it on, you will hear the fan turning on momentarily. One more thing I forgot to mention is that the power supply also came with this user manual, and it has its Kaiweets logo right on top. So the print quality certainly is not bad at all. And it comes in multiple languages here, as you can see. And also it provides the technical specifications. Let's go through this quickly. So obviously this is a 0 to 10 amps and 0 to 30 volts. And also it provides a 5 volts, 2 amps USB output, which is definitely handy. And regarding the specifics of the power supply here, you can see that the line regulation and load regulation are both specified as 0.1%, and which is not bad at all. And also the constant current setting here is also at 0.1%. And regarding the ripple noise, it's alright. It's at 20 millivolts RMS and 20 milliamps RMS. Now notice that this is RMS rating, so I suspect that the actual switching noise could be much higher. One thing a bit of unique about this Kaiweets power supply is that it comes in with this wattage reading output as well. And in my opinion, for a DC power supply, the wattage reading really isn't necessary, as if you know the voltage and amperage, you can just multiply those together and obtain your wattage. But nevertheless, it doesn't hurt to have this display right here. So let's take a quick look at the voltage and current setting accuracy before we putting on any load. And for that, I'm going to just use this BK Precision multimeter here, and I'm going to hook up this stock leads. As I mentioned earlier, these are kind of stiff. By the way, you see that these binding posts here, we do have a bridge between the ground and negative. So this actually negative is chassis grounded right now, but it's a nice touch. You can also, make it float by just removing this ground. And we'll leave the ground on right now, and we will just connect it up, take some readings here. Right now, I think the constant current is set at maximum, so we will leave it as such when we're taking the voltage measurement here. So as you can see that right now 15.7 is bang on at 15.71, and I have no doubt the voltage accuracy would match what is specified here. So let's just turn on to maximum. Maximum is 30.29. Let's go down to around 1 volt just to see how linear this whole reading is. So let's turn on 1 volt, and it's a little bit touchy here, and can't really do the coarse adjustment for that. So it is a little bit of off, compared to the higher ranges. But again, that's just the last digit here, and it's 1.09, 089, so really isn't that a big deal here at all. And one thing I don't particularly like are these fine and coarse adjustment potentiometers. That's not just specific to the Kaiweets. There are a lot of other power supplies utilize the same kind of design as well. And the issue is that you just have to adjust both of these in order to set the desired voltage or current setting, and it's not very elegant. And ideally, you should just put one of those multi-turn potentiometers in so that you can set up your voltage and desired current very accurately. Of course, that adds a little bit of cost, but it's a lot more convenient and also makes the instrument feel a lot more high quality. And now let me swap the configuration so we can measure the current setting accuracy here. I went for the 10 amps range directly, and there's no point for measuring the lower amperage ranges because we just don't have that much resolution here. And off the bat, I can already see there's some issues. For example, right now I'm setting at lowest coarse settings, and if I tune the fine-tune setting, you notice that there's no change on the reading here. So not entirely sure what is going on here, but that's just the first thing I noticed. Now, of course, let's turn on the coarse adjustment here, and let's see at what point. Okay, so we immediately went to 0.71 amps. Now let's see if we can adjust the fine tune. Yeah, we can. So that's interesting. Once we turn on the coarse adjustment, we can actually adjust the fine tune. And so let's turn down the coarse a little bit so to see how granular we can adjust the current. It's really touchy, so I don't think you can adjust it accurately within, say, 10 milliamps, and 50 milliamps may be okay. So the lowest I can get obviously is 0. Right now you can see that it's really sensitive. Actually not sensitive. I turned many turns and now it doesn't do it. Okay. Well, all of a sudden it jumped to 240 milliamps. But of course, this power supply has a maximum current range of 10 amps. So it is expected that you won't be able to fine tune the current output to that much precision here. So let's turn on to, say we want to set up for 500 milliamp. And let's, yeah, no problem. So let's set it to, say, 5 amps. Yeah, this kind of a coarse and fine-tune knobs, as I mentioned, just the same as the voltage settings. It takes some getting used to, and certainly it's not my preferred way of setting these kind of settings. As you can see, you really have to adjust both of these multiple times sometimes in order to get your desired settings. Especially you want the settings to be very accurate here. So I have no doubt we can hit the 5 amps spot on. It just takes some patience. Oh, whoops, actually see, now we are at the minimum of the fine-tuning range, so now we have to turn the coarse down a little bit, and of course when it turned just a little bit, it went a lot actually, the reading. So now you can see we are at 5 amps. And now let's do some load testing. For that I'm using the stock wire here, and yes, as I mentioned earlier, it might cause some voltage drop, but we're more interested in how well the power supply handles the load here. So let's adjust the voltage to something that is even. Let's do a 10 volts here. Oh, sorry, I need to do this. Okay, 10 volts. And what I'm going to do is I'm going to try to measure from the terminal right here so that the voltage reading would be reflected correctly, as even the binding post would have some voltage drop, I would guess. Of course, it's going to be very hard to measure here, and I will have to adjust it when I get it going. So right now it's at 10 volts, as you can see here. And so let me turn on the load. Let's just turn it on, put it at 1 amp here, and no problem at all, obviously. And let's just take a quick look at the voltage drop here, get a sense. and 10.02, no voltage drop just yet. So let's do 5 amps. And you can already see on this meter here, not sure if you can see that, is 9.44 volts. Obviously, that's kind of to be expected here, given the length and also the diameter of the wire here. And let's take a look at the 9.99. So it's already started dropping. Now, that is very interesting, as even though we don't have a 2-terminal, and I would expect that at the terminal reading should at least hold up pretty well. Of course, right now it's only about a few millivolts off, so let's just keep increasing to see at what point we see significant drop at the terminal here. So now we're at 10 amps. So let's just take another measurement here. As 9.95. So that's actually not that bad. So let's see whether or not we can increase a little bit higher. No, it entered the constant current mode. So it looks like the maximum current you can set is really at 10.3, 10.4, that type of thing. And let's see how well the constant current one works here. So let's set it to, okay, that's close enough. Let's set it to 4 amps. Not sure if you can hear, the fan just kicked off here. Now, this fan is, I don't know, it has a very annoying hum, but it does seem that it's temperature controlled, and also it just went down very momentarily, and now it turned off. So that's not a big deal, as for most of the time so far we haven't really heard the fan yet. But that's just something I just noticed. So now we're at 4 amps. Okay, close enough. So we're at 4 amps, and let's reduce the load current to see if we can bring it out of constant current mode here. So let's, yep, no problem. So it looks like that constant current and constant voltage switching is happening correctly here. That is no problem at all. Again, the fan kicked off. But the good news is it's only going to stay on momentarily. So actually now let me increase it to the maximum voltage range, and we'll see how well it handles there. So now let me turn it all the way up. So that's our maximum voltage. Right now it's at 32.05, so that's a little bit above the maximum specified voltage here. So let's just change it to 30, because that's our specification here. So let's try to at least make sure that voltage setting is within spec. Again, 30. So now I'm going to turn on the current to allow maximum current here. So let's turn on the load. And I'm going to go directly to 10 amps. And I'm going to turn on the load. The fan immediately turned on. Of course, in a bit that the fan of my load is going to be turning on. And let's just measure the voltage here to see what we're at here. 29.98. So I'm going to let it run for a while and see if there's any noticeable things that I can see with this power supply. But I suspect it's gonna just be fine. So I actually have had it running for quite a bit, and so the case actually is still cool to the touch, and the power device is inside, which is towards the end if you touch the side, and it feels really cool. So that's actually no problem at all. When we do the teardown, we'll take a look at what is the ventilation setting and how well the heatsink everything has set up. But it appears this unit is quite efficient, and it had held up pretty well so far. Okay, so now let's take a look at the turn-on characteristics of this Kaiweets power supply. And for that, I have set up the oscilloscope, and now is set to trigger single shot mode. And everything is set up. Let me power it on. And as you can see here, it's actually not all that bad. Right now we're setting at the 30 volts output, and you can see that it takes about 1, 2, 3, 4, 5, 6, a little bit more than 6 times 20. So it's around 120 to 150 milliseconds before the power supply stabilizes its output. But besides that, it's a little bit of slow response, but nevertheless, it's a very, very clean rising curve here. Now, the only part I see that there's a little bit of a jump is at the very beginning here. So let me set the voltage to say 5 volts to see if we can see any different behavior here. Okay, so let's do the exercise again. And for that, I think I need to change the sensitivity here. Oops, this is a little bit touchy here to 1 volt per division. That should be fine. All right, so let's start again. 1, 2, 3. And yeah, so now you can see that jump, that's what we mentioned earlier. So now I'm curious, if we reduce it to say 1 volt, what's going to happen? Let's take a look. So let's give it another go. I may need to drop the sensitivity here down to 500 millivolts. And let's just make sure the trigger, let me stop this to see the trigger. Oh, trigger is way off here. So let's set the trigger to be right here. Okay, so let's give it a go. And now we see, okay, so there's no overshot, that's good. But now the curve is actually more abrupt rather than what we saw for the higher voltage output. So it looks everything is actually pretty good. Now let's take a look at this switching power supply's output noise. And please keep in mind that this setup is not meant to show you how to accurately measure the output noise, as we don't have the proper termination here. This Rigo oscilloscope does not have the 50 ohm input, and also I don't have a 50 ohm termination here to accurately measure it. But nevertheless, it should give us some idea as we increase the output current to see the relative performance of the noise. Right now, what you're looking at on the scope is just the baseline. Nothing is turned on yet, and the vertical is set to be 20 millivolts peak to peak. So let me also, by the way, I have the electronic load hooked up so that we can do everything in one scoop. So now let me power on the power supply. And you can immediately see that we have a peak to peak here around 40 millivolts, but again, as I said, we do not have the proper termination, so this is just for reference as a baseline of this power supply here. And we see quite a few significant spikes here and there. Now, of course, if you reduce the bandwidth of the oscilloscope, those spikes are going to be substantially reduced. That said, let me now turn on the electronic load to 1 amp, and nothing significant changes. 2 amps, 3. So let's change it to 5. As you can see, gradually as we increase the current, and we do see the ripple started increasing, which is also understandable given it is a switching power supply. So now let's increase it to 10 amps. And you can see that the magnitude of the noise is roughly twice as that at standby or at no load. So that gives you a rough idea as what to expect when using this switching power supply here. And now it's time for us to open it up and take a look inside. By the way, the case actually is of a very good quality. As you can see here, the holes are drilled very precisely, and even the inside you can see that it is very smooth, and also it is not extremely thin, so the case itself feels very, very high quality here. And what you're looking at here is the inside of this unit. And as you can see, the layout is relatively clean here. And as we mentioned earlier, this board only takes about a very little space underneath here. And if they had made it vertical, they could make the whole unit a lot narrower. Of course, they would have to redesign the front panel here, but it definitely can be done. And I think there are some other variants of this power supply did exactly just that. So in order for us to see everything better, I'm going to attempt to remove this board from this chassis so that we can take a closer look at it. So give me one moment and let me do that, and we'll be right back. Okay, I have removed all these 4 screws, and I can actually flip the board a little bit over. Now, originally my plan was to remove all the cables, but then I noticed that these cables are actually glued down pretty well. And this red stuff looks like it's either Loctite or epoxy type of material. It's extremely difficult to scrape off, and in fact I wasn't able to scrape off the one from the front, so I thought, okay, we'll just leave these on, and at least we can take a better look at the board right now as we can flip the board around. And just by looking at this board, we can see there are actually 3 power supplies on this board. So let's take a look at them one by one. The first thing is we can see the mains power comes in on this end through this line filter here, this common mode filter. And it is going through this, by the look of it, a NTC, so that to limit the inrush current into the circuit here. And then after that, of course, we go through this bridge rectifier. And we go through some filtering, powering our first stage. And the first stage here using 2 MOSFETs as our switching device. And we can see this relatively chunky pulse transformer here. Also, you notice here we have a current transformer that is to do some controls measuring the current flowing through the circuit here. And we see some isolation slots here. And so the isolation slots here are mainly to avoid arcing and high energy vent, as I will point out later. As you can see that this board itself is actually not isolated, but that's what these isolation slots are for. Now, one thing I don't particularly like the construction is if you look at these tall devices here, like for example this toroid, it's really just a wiggle around. And same with this resistor, a power resistor on the output stage here, and you can see that I can wiggle it around. In fact, when I first took out the board, I actually managed to bend that resistor because it was just hanging up here. And another thing I want to show you is this bridge rectifier here, and you can see that it's standing pretty tall and also it's twisted. Now, this is pretty light, so I wouldn't worry too much about it moving around. But nevertheless, you know, you leave the leads this long, which is really not very good practice here. I also want to point out is that you have 2 footprints in parallel for this bridge rectifier, so which means they probably at some point either don't have a fully spec'd bridge rectifier, so they have to use 2 in parallel, or they reserve this board for something else. You also notice that on the high side here, we don't have any ICs, and that is because my suspicion is that they use this purely as a DC-DC converter, and everything is handled on the secondary side. And as we can see here, we have this chip here that is a SG3525AP, which is a PWM controller. So essentially, the regulation is achieved on the lower side with that chip and controlling the pulse width. And of course, we also have a few op amps on the secondary side, and you can see that these are essentially used to control your voltage and current settings, and also for your line regulation, so on and so forth. So that is our main power supply circuitry, and that occupies the majority of the board, at least this corner and including everything here. So the second one you can see starting with this bridge rectifier here, and that is controlled by this TNY280GN, which is a offline switcher, and that power output goes directly to, by the look of it, to the front panel here. So this is that line goes out to, and so apparently the front panel is powered independently as from the rest of the circuit. And the third power supply circuit starts with this bridge rectifier right here. And you can see that, by the look of it, it also uses its own common mode choke here. And not sure why they wouldn't just utilize the main common mode choke. But anyway, by the look of it, that's another common mode choke and its own fuse. And then it goes down to this DK112, which is also offline switcher here. And that one goes to this pulse transformer, and eventually it output from this cable here and powering our front panel USB. And early on I suspected that this Kaiweets power supply essentially are using the same board as other power supplies, and now we can find some of the evidence here. And if you look on top of the circuit board, you will see that the circuit board itself is LW, LWK3010 KDS. So, which means this is the same board used in the long way power supply and possibly other power supplies as well. Another thing I wanted to point out is just how small these heat sinks back here really are. And considering that this unit can output a maximum at least 300 watts of continuous output power. So it's actually quite impressive. The efficiency of this unit must be very, very high. Of course, the heatsink is sitting right in front of this powerful fan, and we also have a very spacious case for the heat to dissipate. So that certainly helps. But it will not be possible without an efficient DC-DC converter design for sure. Now let's take a look at the back of this board. Now, it is not as clean as I had hoped, but especially with these two resistors bulged here. Now, that said, they probably wouldn't have enough space on the other side to put the resistors on. But the problem is that, again, these resistors are mounted with just the leads hanging around, and now the leads here are pretty short, so they don't really wiggle that much. But I just don't quite like this kind of botched down design here. And of course you have a botch wire between here and here. Now that is okay because this is a two-layered board. You may not have sufficient place for routing all your wires, so that is understandable. But again, we have this botched on capacitors here, which doesn't really look all that great. Especially you can see by the look of it, not sure you can see very clearly. Let's zoom it in a little bit more. So it looks like somebody had a shaky hand when soldering the wires. You can see that the solder iron clearly touched this wire, and you can see the solder here, and also just by the look of it, melted insulation casing here. But nevertheless, you know, that is to be expected for this price range of the power supply here. And I just want to comment a little bit more on the isolation slots here. And don't be fooled, just because you have the isolation slots here doesn't mean that this board has isolated portions. And I believe the only reason they have the isolation slots here is to prevent arcing between the primary and secondary, because that's a high power device. And as you saw earlier, that we also have bridge rectifier here and also on the other side. Those are actually taking in directly the 120 mains power here. So we can prove that, and I just trace it for you. And this is our main coming in, and you can see that. Also, it's actually connected. This wire is snaking around, and essentially they are sharing the common main input. And this is the bridge rectifier that I mentioned earlier. So clearly this board has high voltage on most of its sections. If you're working with it, you just need to be very, very aware of that. And finally, as you can see, that the main power supply's output comes from the center bottom of the board to the terminal on the front. Now the binding posts here, I don't mind at all. These are actually screwed on, so these are very sturdy. And we also have an output filter cap right here. Now the wire here, interestingly, I don't think they are thick enough for 10 amps, and that would also explain the voltage drop. As I mentioned earlier, when measuring at the terminal at the front, we do notice about 10 millivolts drop at full power. That said, these wires are very short, so that shouldn't be a significant problem. And here's a view of the front panel and the circuit side. There's really not too much to it, except you can see that we do have a few trim pots here to adjust the voltage, current, and wattage readings, and to make sure that they match the actual output, which they have done it at the factory level, so there's no need to adjust them. Here we have the 4 coarse and fine-tuning potentiometers, and these are single-turn ones. So ideally, as I mentioned earlier, they should just use a multi-turn one so that it will make the adjustment much easier, but that will add to the cost. All in all, it's pretty much what I had expected. While the build quality has more to be desired, the performance of this power supply is not all that shabby at all, and can certainly meet the needs for most hobbyists. For low power electronics though, where precision is required, I would still recommend going with a linear LED power supply. Hope you liked the video. Remember to give it a thumbs up and subscribe. I will catch up with you next time.